Hello and welcome back to the lab. Today on the bench we have the Tech 475A from IBM that we know has a dead power supply. So we're going to try to address that in this video. This was the scope that I used in the first scope, new scope first look video, and we know from troubleshooting this scope in that video, at least slightly, that we have I believe it's a fault in the negative 15 volt rail, if I remember correctly. Odds are good I may not have remembered correctly, given how long this has been off the bench. We'll roll back into the video listings to see exactly how long this has been waiting in queue. So let me get the covers open, and we'll start checking the power supply. Initial thoughts on this, and this is what we're going to check first. Going to look for blown tantalum caps in the power supply. That is the most likely culprit, at least for now, until proven otherwise. But let's see what we find. Okay, this one can be found with a quick visual inspection, and that's actually how I found it. But I'm also going to show how to test these with a ohm meter as well. So we shall see. I will zoom in onto the board, and I'm going to come down this way to the power rails. We'll see if you guys can't spot the cap. Our initial hypothesis was correct. As I slowly pan down, we do have a blown tantalum capacitor. And to make it easy, a little bit easier, since you don't have control of the test equipment watching online, the blown cap is going to be displayed in this camera shot. Now that we have some meter probes with some obnoxiously long leads, I went from a little bit too short to crazy long, but that's okay. This will let me work around the camera. Apologies for the kind of wide angle. I want everybody to be able to see the meter as I'm doing some troubleshooting. So I have the meter in 2-wire ohms range. If I short the meter leads, we have 0.139 ohms of resistance. That's fine. Doesn't matter what that reading is, but I'm going to go from ground, because our problem, let's see, that should show everything. Our problem connection is on the plus 15 volt rail. So if I go from ground to 15 volts, we have 0.51, so 500 milliohms of resistance. So now what I'm looking for the short is I'm looking for the lowest number. So if I'm testing capacitors and I see resistance going up, it means I'm getting further away from the short, and or possibly on this scope not on the right power rail. If I see the numbers going down, I'm getting closer to the short and am for sure on the right power rail. Now, because I know my test equipment and I know how this meter works, it has to switch ranges. I have the meter set to auto, and I can hear the relay in the meter click. So, click, click, click. And I know my meter acts that way on when it needs to switch into the lowest range for troubleshooting. So I can just use my ear. I don't even need to look at the meter while I'm going through. Like, I could test this ceramic disc capacitor right here. I didn't hear a click, and I'm at 7 kilo ohms and going up. So, especially because I'm looking for really low resistances, i.e. a dead short, I know I'm not in the right place. So it really speeds up the troubleshooting just listening for that relay to click in the meter. So that's a little trick. Let's see. We'll pick a tantalum capacitor, and I do want to be mindful of the polarity because the meter is outputting voltage. So I don't want to. It is current limited, but I don't want to reverse polarity into these tantalum capacitors. So we'll test one down here for demonstration purposes. 45 ohms, but also no click. So we know that's not correct. If I test a tantalum capacitor up on the vertical board. No click, 30 ohms. So we're in good shape. If I test my power rail, click, I have a short. So, one of the caps we can test would be up here. Ooh. Trying to do the scope with a busted hand is fun. So we'll test this guy right here. Okay, we have a click. And I'm at 0.7 ohms, so I'm higher than my power reading near the power supply. Or I'm higher than the test points on the power rail near the supply. So that tells me I'm further away from the short because I have to go through more stuff to get back. But that does also tell me that this tantalum capacitor right here is on the plus 15 volt rail. So let's go back to the bottom. And so the vertical board, at least temporarily, we can somewhat rule out. Now, a real quick positive way to rule out the vertical board is to take it out completely. If the short goes away, you're pretty sure the vertical board's got the short. However, that's a lot of work to take the vertical board out. So if I can find it another way, it just makes me faster and the repair quicker. However, on careful inspection of the board, I noticed something. So we have 3 tantalum capacitors here, and one of these things does not look like the others. We have a little bit of melted metal on this one. I'll bet you this is our shorted cap. Let's check. So we have our stripe here, which denotes the positive side. And our meter clicked. 0.3. So this is even lower than the 0.5. I think we found our short. Regardless, this guy needs to come out for more testing. Okay, I have also had a bunch of people ask me how I work on these power rails and how I get some of these repairs done. So we're going to do this one in real time, and there might be a little bit of editing around here. However, we're not going to hide anything. We're going to show the secrets. First off, what I need to do is, as I'm planning this repair, get a pointer. 1, the scope has been off for weeks. I did not power this back up before I took the covers off. I knew the fault was there. Don't need to verify the fault. So I don't need to worry about discharging capacitors and things like that, especially because I'm going to be taking this cover off and exposing the high voltage. So if I had to do that, I would have done discharge procedures, work safely, especially when you expose the negative 3,000 volts. So in looking at this and plotting this repair, we're pretty close to this fiberglass rail. So to make this easier to swap this capacitor out, we're going to pull this rail out, which means I have a coupler here that I'm going to take the set screw out of, and then this will just slide out the front, no big deal. To get to that set screw, I need to pop this cover off. And just to prove there was no funny business, all I did was get the full-size screwdriver to pop this rail out, and these are posit drive screws. Posit drive screws and Phillips screws are not the same. Uh-oh. That's a little stiffer than it should be. Has somebody been in here before? Maybe? No, but that does need to be tightened down. Alright, so we've exposed the high voltage section over here, not to be taken lightly. So, what is this control? Oh, this is our focus control, so it doesn't need to be lined up anything critical. What we are going to do, for working on test gear, having a very small set of Allen keys. This is just a random one that I picked up, but this 0.5, 16, and 5/64ths are what a lot of this tech equipment has in terms of Allen screws. And as I thought, this was the 0.05, so we just loosen that up, and out it comes. Now, that exposes the cap. The real trick on getting this one done without frying up this board or anything critical is these are these coils or are these snubber resistors? Those appear to be coils. So we want to be really careful with the soldering iron coming in here so we don't burn up these coils and melt some things. So what I'm probably going to do is I'm going to come in this way with the iron, pull this leg out, then come over and pull this leg out. I may even cut the cap and to get this one out of here, because that one's going to be kind of a pain. Because we had a tantalum fault, I'm going to be very interested in what the ripple is on this supply as well, because Tech Gear is known for running the tantalum capacitors really close to the power rails. So you'd have a 16-volt tantalum on a 15-volt rail. So there wasn't much headroom, a little too much ripple, overvolts the cap, and even vintage tantalums didn't like that. So we're going to be real careful when we lay this guy down. And we're actually going to work on it from this side of the board. Soldering iron's already heated up. Let me get the vent turned on, because we do solder under the fume extractor. And I also need to heat up the desolder gun, because a good desolder gun is one of the ways I can get at these. Now, we're going to do everything we can do not to mess with the ceramic strips, because we don't need to in this case. So we're going to use a good old-fashioned leaded alloy. 6337. Go. Where are my favorite pliers? These CHP duckbill pliers have been fantastic while I've been working on stuff. The other set of pliers had some stubby needle noses too, but at the moment the bench has eaten them. Alright. So I've added a bit of fresh solder because that will make the older solder melt a little bit better. It's moving. It does not want to come out, though. This one's going to be a pain. Yeah, that's okay. This is where that very fine tip soldering iron that I was talking about in the soldering iron video just really comes in handy. Now what we're going to do is we're just going to walk this part out of here. All right. One side is out. Now, before we go too far, we will check to see if our short is gone. 15-volt rail, 62 ohms. Our short is cleared, so I'm relatively sure now that this was the only shorted part on that rail. So we'll take our part off. All right, here's our dead, come on, focus. Dead tantrum cap with the tantalum metal sticking out of the sides. Now, I've removed the part, but I still need to clear the holes. I haven't cleared the pads yet. A little bit more solder on there. Sometimes you have to add solder to remove solder. That cleaned up nicely. I'm also leaning the desolder gun. I got very close to, but I did not touch this coil. So that was actually pretty tight in there. All right. So what you guys can see, what I can see. Here's our place where we're working. And you can see 2 fresh solder holes, nice and clear. Everything's good there. Now, we have a problem. This one's not marked polarity as to which way is which. So, I gotta look at the schematic, and I need to find out, actually, I can tell. This one's pretty convenient. Alright, so we can tell which orientation the capacitor goes in because we have a pad here which connects to a pad here, which comes into this big fat trace here, comes down here, comes down, down, and we hit our ground pin right here. So we know that this side's ground, which means, and we know that this cap is in the plus 15 volt rail. That means this side's going to be hot for 15 volts. So we have negative and positive of the replacement capacitor. Now, I'm going to dive into the documentation, and I'm going to find out what this cap is supposed to be. This one will be safe to replace with an electrolytic. It is not a timing cap. Yeah, this looks like it's a 25. If I read this right, this is 10 microfarads at 25 volts. Because it's 10 with a plus 25. And the plus side is the stripe, which is normal for, that's another thing, tantalum capacitors. The positive side is marked. Electrolytics, the negative side is marked. Okay, I dug around in the schematics and I found out the capacitor number. So this is going to be some of the horizontal section of the scope, so it's going to be on the A9 board. This cap in particular is C1261, and this capacitor here, right there, is C1263. And we did confirm we have a 10 microfarad by 25 volt capacitor. So let's see what the wall of capacitors has to give me in a good quality electrolytic that will fit the bill. And we have a very comparably sized Nishikon capacitor, 10 microfarads at 35 volts. So we're going to give it a voltage bump, as well as give it the same capacitance. Am I hitting? Oh, that may be on the close to the delay line. Yikes. Okay, so this one's going to be fun to replace. We're going to cut these leads rather short. And this is kind of what I meant in that video about careful lead trimming, is working on the top side of the board. I have to make sure the leads don't short to the bottom of the board once I get the new cap in. And I also need to make sure I get the polarity correct, because getting the polarity wrong would be bad. That's going to do, but now I got to solder it in there. Okay, we have one leg down, so our cap is soldered in. I also checked the height clearance by getting down low and making sure that the top of the cap wasn't going to short to the case when I had everything put back together. It will clear the case, barely. I do not have much wiggle room to work. So now my angles kind of suck to get the other side soldered. So it gives me a feel for how the iron works, how the joints are formed, how long I need, what my dwell time is to get a good solder joint, what's too fast, what's too short, things like that. So if before attempting a repair on a board that would be irreplaceable, it's a great idea to learn your iron and your equipment and your solder, because environmental factors can change how the solder reacts when it's on the board, especially if you're at altitude and the air pressure's significantly different, things like that. All this stuff can affect joint formation, and it's just something that you need a feel for. I've had I have had a soldering iron in my hand for a significant amount of time. This allows me to sneak it into places that would be otherwise inaccessible, which both gets me in and out of trouble. Also, when you're putting together a mechanical enclosure, don't tighten the screws up. Leave them loose so the mechanical enclosure can float a little bit. It really helps with screw alignment. And then once all the screws are put back in, snug everything up. Because I haven't taken 1,000 things apart before. Alright, I'm going to get these way too long leads off the bench and get back to my shorter ones. And then I'll bring everybody back. Okay, short leads in hand. Let's see what we have. I'm going to do ground to 15 volt. 61 ohms. Very cool. Okay, so we've had this scope powered on recently in a previous video, recently being somewhat relative. So let's hook this up to the isolation supply and the current monitor, get this thing fired up, and I have 2 questions that need answered immediately. Question number 1 is, do we get sweep and a trace now? I'm cautiously optimistic on that. Question number 2 is, what's our ripple look like on the power rails? Now, because line voltage is running a little steep in the lab these days, we're going to adjust the regulator on the back of the unit. So to do that, we pop this down. Now, it is unplugged, it is turned off. Do not pull this out when the scope is on. That can actually damage it. Turn this to high regulation. And high regulation is 120 volts to 124 volts. Lab is running at about 123 volts. All right, I've got our HP 200 CD turned on. BNC cable. Turn that all the way down. Turn this all the way up. Turn that to DC. If I remember correctly, we did not get a sweep last time. So, here we go. All right, scope's drawing about 100 watts, 910 milliamps and coming down. We're at 10 volts of division. And let's see, we are triggered. So it's seeing something. And focus is good. And we do have a trace. So let's set this to DC. Pull this way back. And let's give it some amplitude. I have not cleaned any of the contacts or switches or anything yet. So trigger level, boop. I cannot complain about that. Nice crisp trace on this one too, actually. This one's in really, really nice shape. This horizontal control's a little bent. I'll need to adjust that. I don't think that's doing anything. Need to look at the horizontal control. So what I'm going to do now is stand it up on its edge. And we will get all the stuff from up top away, because things like to fall into things. And I do not like having things fall in when stuff is turned on. So now the scope's on, I have to be real careful when I move this around. I do not want to get hit by anything. This has some really big supplies in it. So we've exposed the power board. I may swap this control out with another one that I have, because this feels like that center control, that inner control may be damaged, bent, but we'll look into that. First things first, what's the power supply doing? Well, our 15-volt rail's healthy. Let's check ripple. $150 microvolts of ripple. So that's healthy. How's our negative 8-volt rail? Ripple's fine there. Here's our 110 volt, or here's our plus 50 volt rail. Give the meter a chance to stabilize. It's got to lock into the ripple, or it's got to lock into the frequency. 200 microvolts. Uh, 1 millivolt on the 110 volt rail. So I'm not going to complain about that at all. Everything looks nice and healthy. All right, before we sign off for today, let's investigate this horizontal control, because this is a little funny. I'll push that in. I think this is going to end up having been damaged. But let's see. Oh yeah, that shaft is busted. That control got punched. That's what happened. All right, so we are going to need to replace that control. Fortunately, it's this plug right here. It'll pop out. I'll put a new one in, and we'll go from there. We have a couple of parts units that we should be able to steal one from. The scope is off and discharged since we're playing around with it. Get a ratchet set here real quick. All right, small socket set. And off we come. So this is a dual gang pot. We have the coarse control in the back. Or no, the fine control in the back, the coarse control up front. And it's a 1K, 10K stacked control. Sometimes these are put together with Phillips flathead screws, and you can take these apart, clean them, things like that. This one, you could clean it, but it is not a repairable unit. So we will get another control from a donor unit. Okay, here's the replacement part. It's a 1K, 10K, good Allen Bradley double control. Nice. We're going to make sure it's cleaned up a bit. I think we have the same wire pattern. We do. And the board is marked, fortunately. All right, so we're going to service this up, install it, and then we'll set up the controls. Okay, to line up the controls, I was able to find the scratch marks where the set screw bit into the shaft on the first one. I was able to get that lined up. Same thing for this one. Let's see. Oh yeah, there we go. I can see the indents on the shaft where the set screw bit in. And because these get aligned as part of the alignment process, that is a control that is actually functioning now. All right, let's fire the scope back up, throw some signal at it, and see if our horizontal behaves. All right. Here we go. Our horizontal works. And our fine vertical, or our fine horizontal works. All right, so we have a working control. Everything looks good. So what happens now? It sits on the bench and burns for a while. Not the screen. We're going to turn this down. But I'm going to watch the trigger light, make sure it doesn't go crazy. Now, we haven't replaced any of the trigger transistors or any of that yet. For those that have followed some of my 475 videos, you'll know that the 475 has a whole bunch of transistors that need to be swapped out. I may even need to order some more because I don't have any. But at this point, it sits on the bench and cooks. We got some signal running into it. It's going to burn in and make sure it doesn't have any other problems, because the calibration on these things is long enough. We do not want to have to do it more than once if we can help it. To do a full calibration on one of these without the DMM, it takes about 6-ish hours. The easy way to do it is, well, the best way to do it if you're not running a camera shooting YouTube videos is turn on some music, grab a service manual, and just go. But as it sits right now, we're going to let this thing burn in. Make sure the fan is working. Yep, fan's running. So that's not going to be a problem. So I'm going to throw it back in the case just in case the lab cat jumps on the bench. Luna's been sitting on top of the rubidium standard for a while, so to keep warm. So we will, I'm going to throw this back in the case because I do not need her licking the 3,000 volt supply. That'll also let me test this at temperature as well. So I'll get that done in the background, and then I will let everybody know what we have found out. Oh, changing that from a tantalum capacitor to an electrolytic capacitor. What that's doing in circuit right there is some basic decoupling, so it's not going to hurt anything, not being a tantalum cap. All right, here we go, back in its case, and as long as nothing uneventful happens, we will be very good. Okay, well, the scope has triggered happily all night long. Everything's been good. So the power supply on this guy is going to be finished, and this should be ready for the standard 475 repair and alignment. The standard 475 repair and alignment is replacing the known bad transistors, of which there is 15 of them, as well as cleaning and lubricating all the controls at this point, and then going through a full alignment of the scope, which takes quite a bit of bench time to do. I have done videos on that in the past. Check back in the video catalog if you are interested in more in-depth explanation and repair of those. As always, if anybody has any questions, I will be down in the comments between videos, and I look forward to seeing everybody in the next video. If you would like to support the channel, hit the subscribe button, notifications, and maybe check out the Patreon page. Everything that goes through the Patreon page goes right back into the channel for making videos, getting gear for the bench, and things like that. There are no sponsors of the channel, so the only sponsors that I have are the patrons that help the channel and support the channel. I cannot thank you everyone enough for supporting the channel. So, with that, I will see everyone in the next video.